Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Good afternoon, everyone. My name is Michał Piłaczi, and I will be the host of this very first computational fabrication seminar. The theme of this week is architecture and architectural design. It is my great pleasure to introduce our very first motivational speaker, Hélène Lombois-Burger. Hélène is the R&D project manager for digital design and fabrication at the LafargeHolcim Innovation Center in France. LafargeHolcim is one of the world's largest companies that manufactures buildings, materials with around 7,000 employees. Her role focuses on innovative solutions that create value for customers. Solutions are developed in a collaborative ecosystem across the value chain, including design, materials, processes, and applications. And today she will tell us about the utmost importance of design in the route to market for concrete 3D printing and from a materials supplier point of view. And Helen, the floor is yours.
Thank you very much, Michael. And nice to have all you there. So what you see here, and I will focus my talk on that specific project, is a home that we built in Malawi last November, typically. And I will explain you the main difference that we have between a traditional design process that tends to be something that is really sequential. You start from pre-design, then you have your schematic design, you develop your design, and so on and so forth until you start the construction. And it's something that is just putting the material choice quite late, which means that most of the time you do not benefit from the performances of the material. And the further you go in the project, the lowest is your ability to impact consistent performances, that's the blue curve, and the higher is the impact in terms of cost of a design change. It's completely changing when you are looking at a 3D concrete printing project, because you will make a very upfront global optimization and you will look at everything at the same time. Your design needs to be performance informed and manufacturing informed. And when you will do your design, you need to look at how you will just produce your structure, with which performance of the material and what is required in the specific application that you are considering, typically housing here. So you have a much better optimization of the global process. Now, what happens when you just build with 3D concrete printing is that you need to adapt your design globally and not just rethink it globally and not just adapting it. When you want to design a plane, you won't just put wings on a car. And the thing is that at the moment, it tends to be what is done. If you look at the designs that are mainly leveraged for housing projects, what you have are double walls with a snake in between or some steel connectors to just ensure the stability of your structure, which means that you use a lot of material. And as you have difficulty to integrate some rebars in your structure, you are putting either these loose formworks that you will fill afterwards with reinforced concrete or a separated load-bearing structure. So you quickly understand that these structures are efficient neither in terms of material savings, which means that they won't be sustainable, nor in terms of construction speed, because you have a lot of operations. And what you want to do in the end is something much more efficient, using the benefit of printing that allows you to put exactly the right material at the right place. So how you go towards a more efficient printed structure? The first thing is that you want to save material, but you need to be stable, that it be at fresh state. You have no more formworks, so you don't want your structure to collapse. But also at hardened stage. Here you see a design that we have made for a project of a school in Malawi. You have these two classrooms here, and you want to be able to resist to wind loads. And so we have looked, as you may see on the right corner, at different possible shapes. Obviously, the curved structure has a lot to say in terms of mechanics. The only thing is that when you want to put some furniture in it, it's a little bit more difficult to just fix your kitchen cupboard with this curved wall. So we have looked at different structures, trying to optimize both the quantity of materials that you use in the structure and the ability to have a functionality related to the shape that you use. In the case of the classroom project, the one I mentioned, we were trying to just use it as a benefit to provide some additional functionalities. The kind of more round shape that we use, because it's the one that is the most efficient in terms of material savings, that the one with the least interface, is used to have some more modern teaching modes. Typically, you can have a kind of amphitheater arrangement of the desk, instead of the usual one where some pupils are very far from the teacher. And this can be done with the same number of desks and the same place for every student in that case. The second thing is that we used a kind of crenellated shape to just get the right fresh stability of the structure. And we use this crenellated shape to provide some additional functionalities that can be some shelves inside or some benches outside, or as you may see in the project on the right top corner, you can imagine to put some flower spots if you wish. And the last thing is that we were trying to use afterwards the design, the way that we use, that we patch different classrooms as a protection against intruders, so that you create a kind of closed area in the middle of the different classrooms. How did we proceed with that project? We went from theory, first semester on 2020, with a pre-design optimization, defining how we could imagine these new classrooms, to lab tests that you can see on the bottom left in July 2020, trying these crenellated walls with window parts to check the stability with a new material design to have exactly the performance that was required from the mechanical computations, including the resistance to wind loads. And to the real printing on site in Malawi with quite challenging conditions, over 14 degrees Celsius outdoor last November, with this first classroom that was printed. Now we clearly have some additional routes for further optimization. It starts from optimizing the global structure and also the design of traditional elements. For the time being, we are printing only the walls and using some traditional elements for the other ones. But during our design for the school, we evolved from continuous to isolated footings, using the fact that you will have some rather thin walls and lighter walls. The second thing is that in the future, if you want to develop more of the technology, you should imagine to increase the 3D printed ratio in your whole building. For the time being, as I was just mentioning, you are printing only the walls, which represents a little bit less than 50% of the total on the traditional construction costs. So we should imagine to print also horizontal elements, slabs, roofs, ceilings, and so on and so forth. And the last thing is that we need to optimize the efficiency of the 3D printed walls using some certification approaches. Obviously, for the time being, 3D printing is outside code, so you need to demonstrate that you can use this technology and the performance that it will have. For this first project, we use 3D printed walls as an infill only, and you are having separated load-bearing structures. We choose steel structure for durability's sake to avoid wood that could be kind of with a low durability in this type of countries in which you have low maintenance. Now, what we would like to do in the next projects is to evolve towards pure 3D printed walls that would be load-bearing, on which you can put directly the roof on top of it. The next steps also, if you want to just increase the market of 3D printing, is that you need to multiply. And the difficult thing for the time being is that each time you start a new project, you start from scratch and you need to redesign everything. And there is a real need to rationalize design rules so that you can simplify the approach for a new project. And this can be done typically through the development of parametric models, as it was done for a few applications. For instance, bridges. You see some Nijmegen, I'm sorry, I'm not sure I will pronounce it the right way, a bridge project that was done with Witt & Bos and Summum Engineering. And for that project, Summum Engineering developed a parametric model that allows you to vary the span, the width of your bridge, and so on and so forth. I'm trying to play the video if it would work. Can you see it? Seems okay. And so here you see. So you see how you can move the piles of your bridge, change the number of this, change the span that is just associated. Change the curvature. And that's it. I'm trying to go back to the. So recently, Witt & Bos developed exactly the same model for staircases, and it's something that we should imagine for different types of applications and also for housing, with the ability to just change the dimensions of your building and allow you with this rationalized rules to quickly adapt the design to your environment and your requirements in your specific project. In the way LafargeHolcim is just approaching 3D printing, we tend to focus on mass market applications with load-bearing functionalities, and typically we have three main applications. The first one is wind turbine towers in collaboration between GE Renewable Energy and COBOD and LafargeHolcim. The second one I just presented here is individual housing, and I presented you what we can do in developing countries, but we also believe that there is a market for housing for sure in mature markets, maybe leveraging different benefits, trying to make some more complex structures, integrating the insulation, for instance. And the other ones, the third one is bespoke precast with presently a focus on bridge application. And what you see here is a project that is developed in partnership with X3, Freycinet, and Lavigne Chéron and LafargeHolcim as well. So when you want to tackle the 3D printing topic, you need to focus on its application. And as you are outside codes, you need really to make some good collaboration along the whole value chain if you want to really tackle all the topics that you need to, from pre-design to manufacturing to certification of your building. And that's what we do. We have an ecosystem of partnerships for the three main topics I just was mentioning. On wind turbine towers, with this exclusive collaboration with Cobalt and GE Renewable Energy, and with design being done by Rumble, some process design being done by Optimation, and certification being tackled with DNVGL. In the case of the housing projects, we are collaborating with 14 Trees, which is a spin-off between CDC, English organisms to just boost housing in developing countries, and LafargeHolcim. And the print that I show you in Malawi was done with great support from Cobalt. And this bridge project, as I mentioned, is done in partnership with the contractor Freycinet, the design office Quadric, architects Lavin Cheron, X3 as a 3D printing company, and LafargeHolcim for the material. So you need all these players to be around the table to just develop your application up to the market launch. And the last thing that we do is that we are also collaborating with academics to try to leverage these innovative approaches with especially the LafargeHolcim 3D Printing Housing Hack. It's an event that started end 2020 and that will go up to 2021, a little bit longer than March given to COVID conditions. The principle is that we have student teams centered around their parent university, and they start from reference housing design, and they are reinventing it to leverage the benefits of 3D printing with the ability to either focus on just one specific element, structural element, or on the whole house project as they prefer. And they combine some theoretical engineering approaches with prototyping of their innovations typically. I thank you very much for your attention. And by these words, I hand over to Davide Pellis. Thank you.
Thank you very much, Helen, for the inspiring talk. And I would like to remind the audience to post their questions in the YouTube chat for a joint Q&A at the end of the session. And today, our deep dive speaker is Davide Pellis. Davide earned his master in building engineering at University of Florence in 2014. In 2016, he joined the Applied Geometry group at TU Wien, where he received his PhD in 2019. From last year, he is a postdoctoral researcher at the Geometric Computing Laboratory at EPFL, and his research focuses on geometric and structural optimization for architecture and design. He will give us a deeper view on new classes of quad meshes for freeform architecture.
Well, thank you very much for the introduction, and welcome to this talk where I will present two new classes of quadrilateral meshes, namely geodesic parallel and principal symmetric meshes that are mainly motivated by architectural applications. This work was done in collaboration with Hui Wang, Martin Kilian, Florian Rist, Helmut Pottmann, and Christian Müller. And I will start talking about geodesic parallel meshes. The introduction of these meshes was mainly motivated by the optimization of surfaces for architectural cladding. One of the main costs of a panelization is the realization of the custom molds that are needed for forming the panels. And for a generic freeform surface, we will need one different mold for each single panel. And this can lead often to costs that are not affordable. A well-known strategy to simplify the panelization of a surface is to design with developable surfaces, as was done in this famous building. On developable surfaces, we can dispose cladding panel by bending with an isometric deformation, that means without any in-plane stretching or shearing, a flat sheet of material. And in this way, we do not need any mold for the panelization. However, the design possibilities of developable surfaces are somehow limited. In this work, we want to go one step further and design shapes that are isometric to rotational surfaces. And in this case, we can achieve surfaces that can be cladded by bending isometrically panels that are formed just on molds that are shaping one meridian sector of the corresponding rotational surface. And here with the same color, we show panels that can be formed on the same mold on the left. In this way, we can design really doubly curved surfaces with a reduced number of molds. That is approximately the square root of the total number of panels. First of all, we observe that the classic parametrization of a rotational surface to meridian and parallel circles is an orthogonal parametrization, and the meridian curves are geodesics. And then we also observe that both these properties of the parametrization are preserved under isometric deformations, so both geodesics and orthogonality. Such parametrizations that are orthogonal and where one family of parameter curves are geodesics are called geodesic parallel coordinates. And the name comes from the fact that the second family of curves run orthogonally to geodesics, and then this can be seen as a generalization of parallel curves on surfaces. Well, in the following, we will see how, thanks to these special parametrizations, we can design surfaces that are isometric to rotational one. And we will also see how, since this parametrization carry one family of geodesic curves, this will somehow turn out useful for other architectural applications. Geodesics are locally shortest paths on surfaces, and a characterizing property of geodesics is that the principal curve normal is parallel to the surface normal at each point. And now we want to discretize this parameterization, and then we define discrete geodesic parallel coordinates as quadrilateral meshes where the mesh polylines are discrete orthogonal and the polylines of one family are discrete geodesics. Geodesics will be shown in the following in red. First of all, to see how to discretize this property, let's start from the discretization of a curve, where at the vertex we can define two unit edge vectors, E plus and E minus, emanating from the vertex. We can then define the discrete curve normal as the unitized difference between these two vectors, and the discrete principal curve normal as the unitized sum. And we can observe that by definition, these two vectors are consistently orthogonal. Let's come to mesh now. To a mesh, the first thing that we have to do is to select one family of polylines as geodesics, we show here in red, and then at each vertex we will have the two polylines tangent vectors. Let's see now the conditions for these red polylines to be geodesics. First, we observe that we can define a vertex normal just as the cross product between the two tangent vectors. And then, as we have seen before, the red curve is geodesics if its principal normal is parallel to the surface normal, and then orthogonal to the two tangent vectors. The orthogonality with the red one is already satisfied by definition, so we just have to ask for the red normal to be orthogonal to the gray tangent vector. Then the dot product must be 0. We can express these vectors with the unitized edge vectors. We can expand this product and also express these dot products through the cosines of the angles between the edges of the mesh at each vertex. And then we find this first condition. Then this mesh is orthogonal, is the two tangent vectors are orthogonal, and then their dot product must vanish. Again, we can express through unit edge vectors, expand and express through cosines, and we find a second condition for the mesh to be orthogonal. From here, we can see that a mesh is a geodesic parallel mesh if opposite angles across geodesics are equal. And now we want to see how to use these meshes to design rotational isometric surfaces. And for that, let's go back to the smooth case. And a first property of geodesic parallel coordinates is that the length of tangent vectors of the geodesic curves does not depend on the parallel parameter, so is constant along the parallel parameter. And this means that this parameter, the geodesic curves of this parameterization can be always parameterized at constant speed. And now differential geometry tells us that this surface is isometric to a rotational one if the ratio between the lengths of the tangents of the parallel lines across geodesics does not depend on the parameter v. And then it can be shown that in this case, this surface is isometric to a rotational surface with this standard parameterization where R represents the radius of the parallel circle and H is the height along the rotational axis that can be recovered to this integral. And now on the discrete case, we can first discretize the lengths of tangent vectors simply as edge lengths. And then in this case, this property is always satisfied if the edge lengths along the parallel polylines are constant. And then we can reconstruct the corresponding discrete rotational surface. We can compute the radius of the circumscribed circle of the parallel polygon, and we can also reconstruct the height along the rotational axis simply through Pythagoras theorem. Well, these parameterizations are also useful for the design of developable surfaces. Indeed, let's consider a geodesic strip, that is a strip of surface in between two infinitesimally close geodesic curves, and then we can compute the length, the width of this strip, that is the length of the parallel parameter line in between the two curves. And now a Jacobi equation tells us that if the geodesic curves are parameterized at unit speed, this surface is developable, and then the Gaussian curvature is 0 if the second derivative of the strip width along the geodesic parameter is 0. In the discrete case, the constant speed parameterization can be discretized by asking equal edge lengths along the geodesic polylines. And the discrete Jacobi equation can be implemented by asking that the length of parallel edges is the average of the lengths of its adjacent edges, L plus and L minus. Well, so summing up, we have seen that we can design geodesic parallel meshes by asking to a quad mesh to have equal angles across geodesics. If on top we ask for equal edge lengths along parallel polylines, we design surfaces that are isometric to rotational one. And instead, if we ask for equal edge lengths along geodesics and the discrete Jacobi equation, we can model developable surfaces. And now we show some results that we obtain by implementing these constraints with the guided projection method of Tang et al. Regarding geodesic parallel meshes, the interesting property is that these meshes carry one family of geodesic curves that are somehow fairly spaced over the surface. And we can use this property for the design of geodesic grid shells. Geodesics have the nice property that can be materialized by bending straight strips of material over the surface. And then to design these grid shells, we can start from a given surface. We can dispose on it a geodesic parallel mesh. This will give the first family of curves of the grid shell, and then we can use a second geodesic parallel mesh with a different orientation that will give the second family of curves. And here we also tested this method with a wooden model, and we can see how well the physical model on the left matches our computational model on the right. Now, if we ask equal edge lengths along parallel polylines, we can model surfaces that are isometric to rotational one. And the interesting point here is that we can model surfaces without explicitly knowing to which rotational surface our surface is isometric to. And this can be recovered in a second moment, the equation that we have seen before, if this is needed. We can also use this method in a different way. If we now constrain the edge lengths of the parallel polylines, we can start from a rotational surface and perform an isometric deformation. In this way, we can design architectures like this one, where all surface patches are isometric to the same rotational surface, and then that can be cladded just with molds that are shaping a meridian sector of the same surface. And as we can see from here, we are not restricted to panelization that follows the geodesic parallel coordinates. Another use is the following. We can imagine a semi-discrete rotational surface made of developable meridian strips, each one identical to the others, and then we can imagine to deform isometrically this model. And now these strips will follow the geodesic strips of a geodesic parallel parametrization on a surface that is rotational isometric. And then we can use the geodesic strips of a geodesic parallel mesh to design surfaces like this one, where that can be cladded by bending identical flat strips of materials. And in this case, the strips will have curved boundaries. And now, if the surface is developable along geodesic strips, we can dispose straight strips of material, and then we can design surfaces that can be cladded, for example, by simple words. Well, and now I will come to the second kind of meshes that I will present today, that are principal symmetric meshes. A common strategy to subdivide a surface for panelization is to use a principal mesh that is a quadrilateral mesh that follows the principal curvature directions of the given surface. And this kind of meshes have several advantages. However, if we see these two architectures, we can see that the architects made a different choice. To make them more appealing, they decided to do not follow the principal curvature direction of the surface, but to follow two directions that are symmetric to them. Also, the asymptotic curves on surfaces run symmetrically to principal curvature directions of the surface, and these networks have the property that can be materialized by bending straight strips of material, but disposed now orthogonally to the surface, as is nicely demonstrated by this glitch. And so, motivated by aspects of aesthetics and fabrication, we introduce a new kind of quadrilateral meshes that run symmetrically to principal curvature directions that we call principal symmetric meshes. To understand the geometric properties of these meshes, let's start from a point P on a smooth surface. Then we can select a tangent direction T, and we can intersect the surface with a plane that contains the vector T and that is orthogonal to the surface at the point. The osculating circle of the intersection curve will give the curvature radius Rn. And the inverse of the curvature radius is the normal curvature of the surface in the direction T. And now, if we turn around the tangent direction around the point, the normal curvature will attain a maximum and a minimum. And these are the two principal curvature directions of the surface, called K1 and K2, and the corresponding tangent directions, E1 and E2, are the principal curvature directions of the surface. And these two directions are orthogonal. Now, Euler formula tells us that we can express the normal curvature of the surface as a function of the two principal curvatures, K1 and K2, and the angle between the direction T and the principal curvature direction E1. Let's consider now all curves passing through the point P with the same tangent vector T. Mousnier theorem tells us that the osculating circles of all these curves will lie on the same sphere. And the radius of the sphere is the inverse of the normal curvature in the direction T. And this is called the Mousnier sphere. A Euler formula tells us that two curves that run symmetrically to a principal curvature direction will have the same normal curvature. And then Mousnier theorem will tell us that the osculating circles of these two curves will lie then on the same sphere. And we call a network that at each point run symmetrically to principal curvature directions an S-net. We want now to discretize S-nets, and for that we use a quadrilateral mesh, and we define the osculating circles of discrete curves as circles that are passing through three consecutive points. Then these two circles gives the two tangent direction of the network, and then the vertex normal. And from here we can reconstruct the two Mousnier spheres corresponding to the two polyline directions. In general, these two spheres will be different, but if these two directions run symmetrically to principal curvature directions, as we have seen, the two spheres will coincide. And then the 5 vertices of the vertex star will lie on the same sphere. And we call such a vertex a spherical vertex star. And we define a discrete S-net as a quadrilateral mesh where all vertices are spherical, except irregular vertices. To design S-nets, we can start from a smooth surface, and then we can perform a quadrilateral remeshing along directions that are symmetric to the principal curvatures of the surface. And then we can optimize the resulting mesh for spherical vertex stars. We can also directly design S-nets starting from quadrilateral meshes through an interactive procedure of editing and optimization. And in this way, this can become a design tool. S-nets, on an S-net, we have at each vertex available the Mousnier spheres. And we can use this property, for example, for curvature adaptive milling. Indeed, by tilting a cylindrical tool with respect to the surface normal, we can make the base circle of the tool belong to different milling spheres. Then we can choose one of the two families of polylines of an S-net as the path for milling, and we can adapt the position of the tool to the Mousnier spheres that are available at each vertex. We tested this procedure by milling an aluminium block with a vertical machining center. And here we show the comparison of a surface finished with our method on the top with the best solution that we were able to achieve with conventional methods. With our method, we observe a higher smoothness, and here on the right, we also see a cross section of the surface orthogonal to the milling direction. With this method, we can also mill surfaces with both positive and negative Gaussian curvature. The only limit is that the Mousnier spheres of the S-net must lie all on the same side of the surface. S-nets also come with an associated circular structure that is given by the intersection of spheres that are sharing a common edge. And if we substitute these circular arcs to the edges of the mesh, we get a structure where all the arcs that emanates from a vertex lie on the same sphere. And then they have the same tangent plane at each vertex. The layout of this structure is strongly dependent on the variation of radii of spheres among the vertices, and here we show a case where this structure yields a very regular pattern, but this can be a field for further research. We can also ask for other constraints on an S-net. For example, we can ask for sphere radii with a constant radius at each vertex. Now the network will have constant normal curvature at each vertex. And so we can use this property to design grid sheds like this one that are made by bending circular arcs with identical radius. And here we tested this with a paper model, and down you can also see some of these congruent arcs. And this property can be used in architecture by using, for example, flexible materials like wood or metal. on a generic S-nets, the angles between the network curves varies among the vertices, but we can also design S-nets with a fixed prescribed angle between the curves, like shown in these examples. And now let's think to design an S-net, constant sphere radii, and also constant network angles. Euler formula in this case tells us that the two principal curvatures K1 and K2 follow a linear affine relation among the vertices. These special surfaces where the two principal curvatures are in some functional relation are called Descartes surfaces, and these can be interesting in architectural applications because on these surfaces the two principal curvatures are constant along a family of curves on the surface, and then along these curves we can somehow dispose panels that have a similar shape and then that can be formed on the same mold. And so in this way, this is another way for reducing the number of molds of a surface that will be here approximately again the square root of the total number of panels. And here we show two architectural applications. In these cases, the panelization is following the principal symmetric mesh that we use for the computation, but this is not necessary. We can also use other layouts. Now, if the sphere radii are constant at each vertex and the network is orthogonal, Euler formula tells us that the mean curvature of the surface is constant at each vertex. And the Musnier sphere is now the mean curvature sphere of the surface. And so, with orthogonal nets with constant radii, we can design constant mean curvature surfaces. And we can control the mean curvature through the sphere radii at the vertices. Now, on orthogonal networks, if the spheres degenerates into planes, we can design minimal surfaces, since the normal curvature vanishes. S-nets in general have non-planar faces, but it is possible to design special S-nets where faces are planar. To understand it, let's consider the Dupin indicatrix of the surface at a point that for positively curved regions is an ellipse with axis aligned with the principal curvature directions, and the length of the axis is given by the inverse of the square root of the two principal curvatures. Well, it is well known that a quadrilateral mesh with planar faces must follow a conjugate network on the surface, and the only conjugate network that is symmetric to the principal curvature directions is the so-called characteristic conjugate network that is given by the two diagonals of the axis rectangle. And unfortunately, these two directions exist only for positively curved surfaces. And here we show an architectural application of these meshes that can be materialized, for example, with flat glass panels. And then finally, I will briefly talk on how we can further use quadrilateral meshes to optimize surfaces for paneling through isometric deformations. Let's start from a spherical surface patch, here shown on the left, and let's deform this surface isometrically. On these resulting surfaces, we can dispose by isometric bending panels that are all formed on one single mode. And this is because on the sphere, the two principal curvatures are constant at each point. And then we can design an architecture like this one that can be cladded by producing only a single mold. We can go one step further, as we have seen at the beginning of the talk, and use now rotational surfaces. In this case, the two principal curvatures are constant along the parallel circles. And along the images of these circles under the isometric deformation, we can dispose panels that are formed on the same mold. But we have seen that also on Weingarten surfaces, we have a family of curves along which the two principal curvatures are constant. And these surfaces can be, a subclass of these surfaces can be designed with S-nets with constant angles and constant radii. Then along these lines, we can dispose similar panels that are formed on the same mold. And now we can expand the design space of Weingarten surfaces through isometric deformations. And now the panels that are in the images of these curvature isolines can be formed on the same mold and can take their shape by isometric deformation. The isometric deformation can be easily implemented with the method of Young et al. That works through the preservation of the lengths of the phase diagonals and of the relative angles. And then we can implement these constraints directly on the S-net that we used for the computation. And here, this is an architectural application of these surfaces where for panels we have to use flexible materials. With this method, we are not restricted to quadrilateral patterns, but we can use every kind of pattern. The important thing is to map back the pattern to the corresponding isometric surface to do the panel clustering and to design the molds. And this I've finished, and thank you very much for your attention.
Thank you very much for your talk. And we will now start the joint Q&A session. And we have a first question for Helen. And what is the potential of 3D concrete printing towards more environmentally stable construction? How does the technology compare to traditional methods at the moment?
That's a very good question. And that can be a tough one. If you are looking at housing only and you compare to concrete blocks is a very good solution. You have a porous concrete that is used inside with low cement content, and it's hard to compete. Nevertheless, you have something to say because, as I mentioned, you have the ability to put exactly the right material at the right place. And you can see that, so I would say it depends a lot of the application and the context, and you have different strategy. If you look, for instance, at the bridges project, you have the ability to put some, to vary the cross section and to put some large cross section just where required, instead of pouring something that is just rectangular because it's easier in molds. And in the bridge project that I mentioned, you can save up to 60% of material. The same goes with the housing. For sure, you should avoid these double walls that are really inefficient. If you have no additional functionality that you can hope, if you are not using the cavity to just pour some insulation, it's useless. And I guess that part of the future of 3D printing goes in evolving from very high performance materials to just the right performance one, Second, using bigger aggregates to just limit the paste content and to really have an environmental friendly material with optimizing the footprint of this material as well. And also looking at alternative supply modes that are very important to just try to minimize transportation and see the different ways you can just produce the different things that you will use and transport them to site. And you can make huge savings for that. So it's not forgiven. You need to just engineer it. But if you do the job well, you can save quite a lot.
Thank you very much for the answer. The next question is for Davide. And the question is about the scale of the examples that you were showing of your work in the real life, and how does the material of them affect the meshing that you have to do to perform them in larger scales. So, for example, the paper prototype, would it scale to a large surface, or would the meshing have to be adjusted to do so?
Well, the mesh itself, we should, of course, consider the allowable deformation of the materials, and for that I didn't show it, but somehow when we use, for example, geodesic parallel meshes, we can estimate, for example, some errors, some strains that we have in the panels, and we can take them into account in the optimization. And this is for paneling, but of course also for other methods where we use these bending strips. These are tested in, let's say, small scale architecture, because when things become too big, the energies of bending and so on are very strong, and so this might be a problem.
And would adjusting the meshing help alleviate this problem?
Well, it's not the mesh itself, I would say, because the problem is given by the shape itself. So if we have too high curvatures of the resulting shape that does not allow this isometric bending in a reasonable way, this will be not possible. But it's more connected to the shape than to the mesh.
Thank you very much. Then I have a question for Helen, and it's a follow-up on the 3D printing materials for concrete that are not yet suitable for load-bearing structures, that they are not yet certified. In traditional manufacturing, concrete is usually certified or reinforced with metallic rods. Do you think something like this would be necessary for load-bearing structures from 3D printed concrete, or is there a way around this?
You have different ways around it. I think in the case of the housing, if you just wish to substitute a masonry wall, you do not require very tough performances. You need to select carefully the area you choose, and typically not to start with seismic areas typically, but concrete as it is could be part of the jobs. In other strategies, you need to have some alternative reinforcement strategies. And for instance, in infrastructure projects, the complementarity between 3D printed concrete and post-tension is quite good, and is leverage for these projects. So I would say there is no one size fits all. You need to find the right solution, but it's typically one of the big challenges that we have to address if we want to crack mass markets afterwards.
Thank you. Then we have a very technical question for Davide. So is there work to approximate a given surface with a Venn garden surface without specifying the relations between the K1 and K2 in advance?
Yes, this is something that we are working on. Somehow, also when we use S-nets, we do not specify exactly the two curvatures. We just specify the relation that they will have. And but we are also working on more generic methods that are also allowing to design Venn garden surfaces without prescribing any kind of relations. Somehow that these relations is emerging naturally from the optimization.
And a follow-up question to that, can we expect a faithful approximation if we allow complicated Weyl-Garden relations, such as when the two curvatures are equal to 0, or when there are multiple components?
Yes, this, I mean, the space of these Weyl-Garden surfaces is still largely unknown. So we don't know exactly how much we can somehow push a surface or get something complex. But yeah, it's a complex optimization. It's a difficult optimization, and the convergence is not always easy. But yeah, I would say that we still don't know what we can exactly do.
I see. Thank you very much.
I don't understand it.
And last question for Helen. The 3D printing housing hack sounds extremely exciting for students to start working in the area. Is there still options for students to join, or are there similar initiatives planned in the future?
Yeah, I would say it's maybe a little bit late to join this one. It's a pity if you hadn't the opportunity to do it. We try to make as much advertising as possible. But yes, we definitely have in mind the idea to make new events in the future. And if you have an idea, reach us out before we act. We'll be glad to discuss it and see whether we can do something together.
Okay, so I would like to thank very much both of the speakers again to show up today. And I would like to remind that we'll have a short unofficial discussion at the Discord after this session. And I would like to invite all of the people watching to join us in there. So thank you very much and have a nice rest of the day.
Bye.
Bye.
Bye.